I think we can start because according to my watches, 10 minutes passed. So, okay, good evening, everybody. Let's start our discussion session on phase diagram on the context of the heavy ion collisions. Just for those who just linked to us or missed some talks, let me briefly remind what was in our session. So we had 5 talks, and actually the topics of these talks, it was rather different and all very interesting. And because in this case it would be a little bit difficult to make homogeneous discussion, I propose we organize the session in the following way. I will start with a short introduction just to warm up discussion and to briefly remind the main issues of each talk. And then we will start discussion talk by talk. It means we start with the first speaker and then we come to the second and so on. Of course, in this case, we limit discussion for each of the speakers, but it would be absolutely fair because then we cover all topics which we heard today and could discuss open questions and issues since our discussions during the talks were really very short. Okay. And in the end, if some time would be left, of course, we can make iteration and so on. Okay, let me start with some very general, sorry, that was not what I wanted, with some very general remark. Of course, in this workshop, we intensively discuss different theoretical approaches to achieve our knowledge on the phase diagram of the QCD. And but finally, the final answer still lies with the experiment, because in the end, we have to compare our theoretical knowledge with the experimental data. And experimental data are basically comes at least in this region of the phase diagram for larger temperature and relatively large baryon chemical potential and baryon chemical potential in all this area from the heavy ion experiment. Of course, at very low temperature and very high baryon chemical potential, we nowadays hope to obtain information from the neutron star, gravitational waves, and that is another interesting topic which has been discussed during this workshop. But in our session, we will concentrate on the heavy ion collisions and what it can be provided, what kind of knowledge we can obtain from that. And of course, let's start with the key questions of heavy ion collisions. And one of the very important question, what are the properties of hot and dense matter created in heavy ion collisions? And also, what are the degrees of freedom and their properties and interactions? And here we are definitely lacking from the knowledge from fundamental basic theory of QCD, which is realized in the lattice QCD, because as we see from the plot below, which has been shown by Jana Günther, so nowadays lattice QCD can reliably provide us knowledge up to finite baryon chemical potential on the level of 400 MeV. And what's happened after that, it's already relies on a different effective model and other, let's say, phenomenological model and some approximations of the QCD. And what is the other important issue that actually lattice QCD cannot provide us directly information about degrees of freedom and their properties. And that's what we have to learn all by building maybe some kind of effective model and compare with finally experimental data. And but what we definitely know already from such type of approaches that, and also in their comparison with experimental data, that QGP is strongly interacting liquid. And that's, we know that closer to the critical temperature, the coupling constant grows and they come definitely to non-perturbative QCD regime. In some sense, it changed our paradigm, which we had in the last millennium when people were talking about the QGP in the beginning as a, let's say, gas or weakly interacting particles. And nowadays we are talking about strongly interacting liquid. And it's a completely different viewing of what's happening. But by the way, in the lower part of the diagram, we have a hadronic world, which is also incredibly interesting because we create a hadronic matter, highly compressed, and it's a hot and compressed medium. And here we have another interesting effect, for example, such like chiral symmetry restoration effect. And indeed, one of the key questions discussed extensively in this workshop, what is the origin of phase transition, if it is at all? Is it crossover or is it a first order? Do we see critical points and so on? And another important issue, it was also related to the discussion about the influence of electromagnetic fields, because as we know, in heavy ion collision, we produce the strongest electromagnetic field known in our reality, and it might lead to some kind of polarization phenomena. And of course, questioned what would be traces of all of these phenomena in heavy ion observable. But again, in heavy ion, we measure spectra, we measure rapidity distributions and some flow and so on. But in order to obtain knowledge, we have to compare with the theory, and the basic theory QCD relies on a lattice, but definitely it cannot be solved, as I said, with the full beauty nowadays, and we have to rely on effective models. And in order to compare heavy ion data, we need definitely to cover very complicated dynamical evolution. And for that, we need, because of that, we need the transport many body theories. And another important issue, what kind of observables we can address. And as I mentioned, in experiment, we measure spectra, bulk observables, multiplicity, flow. We measure electromagnetic observables, dileptons and photons, cluster hypernuclear production. We measure hard probe. And the idea is all these particles, all these probes are emitted from different time of the reaction. And because of that, we hope to reconstruct the full time evolution of heavy ion collision and obtain knowledge on the different phases of our reactions. And again, what do we study? We study different systems, and that is very important. We start with elementary proton-proton collisions and proton-neutron, very hard to realize experimentally. Usually we have experiment on light nuclei on a deuteron. But that is of fundamental interest itself. And for heavy ion collision, it has another important issue because it provides the reference frame and some input information to study heavy ion collisions. And we study also proton nuclei, pion-induced reactions, and that's in order to obtain the knowledge on cold nuclear matter effect. And of course, the main issue, we come to heavy ion collisions, making a scan from light system to heavy system. And here we have all beauty of our knowledge, all many body effects, some isospin phenomena, influence occasional state, critical point creation of quark-gluon plasma, and so on. But again, we have to compare with the theory. And some of such theoretical approaches has been presented today. And in the first talk of Olga Soloveva, she was telling about the properties of the hot and dense QGP based on dynamical quasi-particle model, which has been developed in propagator representation, and which is emerging lattice QCD equation of state. And because of the properties of quasi-particle, you can extrapolate to finite mu and study the crossover behavior of different transport coefficient and so on. And Olga also was telling about the latest work with another group about the PNGL model, which is one of the advanced PNGL model, which fits the lattice QCD equation of state at finite baryon chemical potential and has a first order phase transition. And also Olga presented the realization of the DQPM model for the heavy ion collision, and when it's implemented in Parton hadron string molecular in string dynamics. And here she showed how we obtain T mu behavior and time evolution and consequences on observables. So this would be the first topic for our discussion. The second one, it was a talk by Volodymyr Vovchenko about probing the QCD equation of state with fluctuation of conserved charges. And here Volodymyr created this nice transparency for our discussion. And key question is, how to relate event-by-event fluctuation in heavy ion collisions to lattice QCD and ground canonical susceptibilities. And the ingredient of his model is hadron gas model, which is a match to lattice QCD at freeze out. And in this case, also he developed the particularization routines to merge to hydrodynamical approach. And as a result, he provided quantitative analysis of fluctuation in heavy ion collision and obtained a significant effect of global baryon conservation and thermal smearing. And I don't repeat, so you that would be written here. Okay, then we had experimental talk with a review on the direct photon production from proton-proton to proton nuclei and heavy ion collisions by Dmitri Peresunko. And here he actually already raised the question, and the main, I will not read all of them, but we come to this slide in our discussion, but the main question is how to understand the experimental data on direct photon production and how we can obtain, how we can compare with the theory, and he claims that the theory is also theoretical approaches, hydrodynamic and transport is a missing yield or flow, and it's very difficult to describe all observables simultaneously. And he discussed a few attempts how to improve the situation, but unfortunately they failed also. So that's very interesting topic. We come to that, and then it was also talk related to dileptons, already to dileptons, but to electromagnetic probe by Chihiro Sasaki. And she described how to probe chiral symmetry restoration with dileptons, and how do we see the signals of chiral symmetry restoration in dilepton measurement. And here she proposed a model which describes the axial vector mixing. And because of that, we have chiral symmetry restoration effect. And due to the mixing, the spectral function at finite density for rho meson and omega, that's obtained very particular structure, which we explain, and also for phi meson. And finally, we hope to see such effect in dilepton rates. And the last talk by Evgeny Zabrodin, who presented transport model approach, UQMD actually, for lambda polarization. And the main idea is that polarization could be coupled to the vorticity, and vorticity you definitely can calculate in the transport approach. And he obtained quadrupole behavior of vorticity. And here in this plot, he explains the different origin for production of lambda and lambda. And here he showed the main result, how polarization of lambda occurs as a function of square root of s. So that was our talks for our speakers for today, presented this talk. And I propose we now come to Olga. And now we can start our discussion. I think I wanted to see rising hands, and please, if you want to say something, raise your hand. I see Oleg Teryaev. Please, Oleg, unmute yourself, ask question.
Thanks. Unfortunately, I had a lecture and missed the talk of Olga. And I have a question to you. What about the possibility to study the anisotropic transport coefficients, like, say, anisotropic conductivity? Because in principle, I know that in your earlier papers with Wolfgang, there were some equations which allowed to do anisotropic calculations, just to calculate, say, conductivity in different directions, say, if there is a vorticity or magnetic field.
In principle, we can do this, but in order to do so, we need to parameterize our dependence on magnetic field. So this is effective model. So in principle, we can do this in for DQPM, But then we need to parameterize this dependence in the masses. So,
Oля, I think the question was related more to PHSD, right, Oleg? So to dynamical transport
actually,
approach.
well, my another question was maybe, well, glad to see you, Oля, also like
okay.
Lena. So just my question was also, you use two models, right? Are you comparing them or somehow them?
We don't use two models.
Or they're more complementary?
So can I comment on this?
Sure.
So for PHSD, we use only dynamical quasi-particle model, but I show the result for DQPM and for PNGL. And we compare this model because it's interesting. They have different effective masses and different degrees of freedom, but actually the transport coefficients are very close. And the idea is that dynamical quasi-particle model is rely on the entropy density as an input. So we parameterize the model using the entropy density. And in principle, we can use not lattice QCD entropy density, but entropy density from other model as a PNJ model. And actually this is what I'm doing now. So, and the idea here that we can go higher in μb, and then we will consider also these properties of quasi-particles, such as transport coefficients near the critical endpoint. So I can show you actually my result for the comparison of these models.
I can stop sharing. Yes.
Do you see my screen?
Yes. Okay.
So, okay. Oh, do you see? Okay, just in brief recap for Oleg, that here I showed the dynamical quasi-particle model results, and it's RTA approximation of Boltzmann equation. So, and here later we compared results for Polyakov-Nambu-Yon-Lazinium. Here, for example, the results are shown for the Polyakov loop Nambu-Yon-Lazinium. This is red line, and for DQPM, this is dotted green line. And you can see that in the vicinity of the phase transition, they are really very close. And even they have a different μb dependence. The results are the same, that shear viscosity is increasing with the increase of baryon density. So
that we find
and also,
yeah, okay, sorry.
So that is also the same for the electric conductivity. While for electric conductivity, the difference are maybe bigger, because here you know, more quarks degrees of freedom play a role than the gluons. So it's but anyway, the temperature dependence are very the same. You can see that these lines are completely like a parallel lines. This is you can describe this dependence as a t-squared. So
but you use the same equation for both models, right? Right, which is on this slide, which is written on this slide, right?
Yes, but for PNG model, the distribution functions is taking into account the Polyakov loop. So it's a modified distribution function.
Yeah, and I think so. Where, how, I mean, how anisotropy can appear here? Because here it looks like this is already rather isotropic. This equation.
That is rather isotropic, but such effect could be in some things calculated in transport approach. But it's
yeah, because I know that in principle it's because this is already somehow isotropized in a sense, right?
Exactly.
So just
yes, that's true.
But
so, but there are And probably this equation is easier to use, right? It's more compact. It requires less computing time, probably like that.
Yes,
so you are using
sure.
it.
But
Yeah,
in principle,
but in a sense, anisotropy it can be interesting also because correlator, just as we discussed, it's may related to the polarization, but this requires indeed something anisotropic. If it isotropic, there is no direction with respect to which one can measure just polarization. I wonder maybe somehow the distribution functions can somehow carry some. If you add in the distribution, just a simple idea, if you add here term proportional, say, to angular velocity times momentum, like it is done in statistical calculation, maybe also can be a way to do some anisotropic calculation.
Yeah, actually, in principle, we can do so. We can modify the distribution function. And actually, I think I saw the NGL calculation for the anisotropic quark-gluon plasma.
Okay, I think we have to come maybe to other questions because we have
okay,
5
yeah,
talks.
sure,
Don't
Okay.
forget.
Thank you,
And
Oleg.
just a
Thank
second,
you.
it was one
Yeah.
hand. Nugzar wanted to ask some question. Please ask question.
The question to the first talk was, what is the nature of the quasi-particle? And we know at different states what is particle in the perturbative time or scale. We know the quarks and gluons and so on. Then perhaps excitation and so on. At last talks, Evgeny showed some candidates for the quasi-particles like Lund string and so on. My comment is the following. Let us remind what was the main statement of the first publication of Alice, collaboration of LHC. They stated few sentences. Not any generators describes multiparticle data as a whole. Only one distribution may describe these data, namely negative binomial distribution. Let us imagine what is the physical picture beyond this distribution. Very clear, very nice picture. This picture is the following. You have integer number, some number k, of independently radiated of hadrons sources. This radiation law is a geometric or Planck law, or black body radiation of hadrons. This is very clear picture. Quasi-particles at the last state of the hadronization, we know they are black body radiated. We even count that number of sources. This is exactly the parameter of the NBD, negative binomial distribution, parameter K. Even more, we can identify place of that sources, and this is the good job for the future analysis. Thank you. That was my comment.
Okay, very nice. Let's say, but here, I'm sorry, idea is a little bit different. So the goal is not to fit something with binomial distribution or polynomial, but to understand the nature of strong interaction, and in this case, the meaning of these degrees of freedom, to understand the nature of degrees of freedom. So, and that's why dynamical quasi-particle model is one of the effective model, actually rather successful, which is based on also fundamental things like propagator representation, and as soon as you write it, you do that in an effective way. You don't make resummation and solve QCD in this case, but you can introduce few parameters, which is ansatz, and to catch the full beauty of the lattice results with such approaches. So, Oля, do you want to shortly comment, because we have to come to other talk?
Yeah, I can shortly comment. Thank you for your comment. It was very useful. But yeah, the idea here is that it's just simple model to describe the finite density, not the Alice data, where the density where at finite may be, where we don't have PQCD models or hard thermal loop calculations. So, and as Elena said, we can parameterize our model using lattice equation state. And here you can see that the dynamical quasi-particle model parameterized at maybe equal 0 can reproduce lattice data at non-zero maybe. So it's just simple model which can describe your microscopic properties. And also, actually, we compared our coupling constant to some lattice data, and you can see that there's some calculations for an f equal 2, and our coupling constant, which we have extract from the lattice QCD data, are very close to these lattice QCD calculations. And as you can see, actually the coupling constant drops very fast. So, and
Yes.
this, I agree that it's not first principle calculation, and maybe
I
we
see
cannot
even the
rely
value
on
of 3
the
is reached.
on
Very
the
nice.
on actually in the we cannot rely on the weak coupling region near to C. But unfortunately, there is no other way. So in our model, we just reproduce the latest results. So our coupling is somehow resummed coupling, and our quasi-particles is dressed particles. So, and they are living mostly at low temperature. So at high temperature, we have a very good agreement with the hard thermal loops. So,
Okay, Olga, I think thank you very much. I'm sorry, we have to definitely come to Vladimir talk. And Vladimir, are you with us?
Yeah, I'm with you.
Super. So I can share a slide to remind the key questions which Vladimir addressed, but please ask questions to Vladimir now. Please raise your hands or unmute your mic. Better raise your hands if you want to ask Vladimir something, and let me come to my questions, because I also still people are thinking. So Vladimir, can I ask you some might be very, let's say, naive question, because in your model you were introducing the repulsive core for baryon-baryon and baryon-antibaryon interaction, right?
Yes, well, not quite. Baryon-baryon, antibaryon, antibaryon. So baryon,
Yeah, sorry,
yes,
it was written in my notes correctly. I pronounced it wrongly. It's too late already. So, okay, sorry, but how to be with the meson-baryon and meson-meson type of interaction? Would it be needed in your model, or how about that? Can you comment?
Yes, well, it's an option which you may consider if you want, but if you want to do a minimally intrusive, as I said, extension, then for net baryon fluctuations, you don't really need that to incorporate this. And another angle which you can use to look at it is to look at what we know empirically about scatterings of mesons with baryons, of mesons with mesons, and there is I think a nice and fairly classic work by Prakash and Venugopalan from about 30 years ago, where they show that in most cases interactions are mainly incorporated by resonance formation. This is true for pion gas to large extent and for many meson baryon cases. But you can look for this possibility maybe if you find a good motivation, for example, not in baryon number susceptibilities, but in charge, baryon charge or charge strangeness correlations and so on. But I would say this is and that this is not really needed right now, in my view.
I see some question from Dmitri Peresunko. Please, Dmitri, ask your question.
Dmitri Peresunko. Okay, Vladimir, I would like to ask how do you interpret your excluded volume about 1 Fermi per
I'm sorry, Vladimir, if you want to share a slide, I can stop sharing these questions because maybe you want to share your talk in order to explain something, yeah? I stop.
Yeah, okay.
Yeah, please do that, just to remind people what was the topic of your discussion.
Okay, so let me see if I still have my slides. Okay. Well, one cubic Fermi you can view as a eigenvolume of a composite object.
Vladimir, can I finish my question? So
Okay.
if we look at the interferometric results from Alice, at the stage of decay to final particles, we have density about 0.1 particle per cubic Fermi. So it is the end of fireball when it decays into the final particles. It is 10 times smaller than your volume, so somehow it should be compared.
Okay, but you are talking about the density of particles, or?
Yes, density of particles.
Okay, but this is eigenvolume of a particle, so it's a volume of a single particle. The density can be very small, and if the density is small, the effect will be smaller generally, and you see and to see this effect, you need to go to observables which are sensitive to this effect, like high order cumulants, which I have considered here.
So you consider this as a completely arbitrary parameter which has no physics meaning?
No, it's an eigenvolume of a particle. It's not a point particle, but a particle with finite size. This is the
size.
You cannot put 10 particle if volume per one particle is 1 cubic Fermi. So this I don't understand.
Wait a second. Why is it a problem? Which volume? No. You mentioned density. Which volume? Which total volume do we have?
It is estimated that density of particles is about 10 particles per cubic Fermi. And you
10
have
particles for cubic Fermi. Oh, wait. Are you talking about baryons or mesons, or all particles?
All particles.
Okay. No. This is fine because mesons are point-like. You are talking about meson-dominated matter.
Okay.
And they are point-like.
If we exclude mesons, then we will have few baryons per cubic Fermi at the stage of decay.
No, not few. The proton to pion ratio is less than 0.1, so you will have less than 1 baryon per cubic Fermi at LHC.
Yes, it's good estimation of the volume of the baryon.
Yeah, you can also think in terms of a radius, so a linear size, not the volume, and this would be something around 0.4 Fermi, the radius of a baryon. And this is, I think, if you look at empirical potentials of nucleon-nucleon interaction, this is in the same ballpark, typically. So mesons are point-like, therefore large density of hadrons, which are mainly meson, is not an issue here, at least in my view.
Okay, I see. Thank you.
Lena, this
that
is
was
Chihiro
a comment.
Sorry,
it was a comment. Just a second. It was a question or comment
from Chihiro.
First, it's from you, Kirill. Yeah.
Yes.
Oh, then please just ask yourself. Yeah.
Okay, Volodya, just one cubic Fermi is not eigen but excluded volume. So 4 times of eigenvolume.
Yes, you're right.
So,
well, in the classical picture, at least.
Yeah. Because
I mean, I don't literally.
But I
say
think
that it has to be a sphere. It's just a particle with finite size. You can think of it as a sphere. It does not have to be a sphere.
So. I think the young guy simply mixed, the volumes and Okay, but you're right in this sense. Thank you.
Thank you.
Okay. I don't see other hands. But Vladimir, I have still a question to you. Could you please go to slide number 13, I think.
This one? Oh,
Yeah, 13.
I moved. Yeah, it just moves.
Sorry. Yeah, this one.
Fast. Yeah.
It's related to your this practical routine for particularization. And when
Yes.
you this picture which you illustrate how you make a granularity actually. But what is the size of your cell up to? What is the criteria? How you should discretize your space?
Yes. So the criteria is that well, it has to be smaller than the acceptance, where you eventually want to measure fluctuation, and smaller than the thermal spread. So this is one criteria, but it has also another criteria. The cell size has to be such that the physical volume is large enough that we can talk about approximate thermodynamic limit.
Okay.
So this means that the volume of a cell has to be of order 100 cubic Fermi or larger. This is one requirement. And the rapidity width has to be smaller than 1 unit. So these are parameters which, which we have to put at some point. But I have tried varying them and in these ranges which I mentioned, and the results did not change.
Does it depend on energy, I'm sorry, or it's more or less universal, or would it be different, this criteria for the size at recoil HC, or how does it work?
Yes, so the size in the rapidity, which I mentioned, is more or less universal because it's determined by thermal smearing, and thermal smearing it's roughly the same temperature we have, around 150 MeV, which determines. We can things might get problematic at lower energies because we will run out of volume, right? So the volume will not be large enough for us to neglect the finite size effect, so to say. The fact that eigenvolume or exuded volume of a single particle may become comparable to the volume of a cell. So we need to avoid this situation. At LHC, this is very nice because the volume is very large. But I think when we get somewhere to low SPS, we might encounter this problem.
Okay, thank you, Vladimir. Okay, thank you, Vladimir. I don't see other hand. Let's come to the talk of Dmitri. And well, Dmitri, maybe you can share your talk yourself, because I'm pretty sure it would be some questions concerning your experimental results. And you also had a nice transparency with the questions. I can do that for you, but...
Okay, 1 second.
Yeah, sure.
I'm looking for this window.
So, and please prepare the questions for Dmitri, because there definitely was some questions which we, thank you. Okay, please raise your hands who wants to ask questions. Let me see if there is something in chat. Actually, yes, Nuxar, can you ask your question? Please.
Yes, it was time to switch. You analyze photons from different stages of the evolution of that intermediate state. And it's very nice to know at every step how photons show the pictures of the evolution. Maybe there are other signatures also. So I'm just speak to hit up other questions. I have not my own.
Okay. Well, maybe I can ask you the question. So it's more related to experimental subtraction of, let's say, direct photon contribution, because from exclusive, you have to subtract a lot of decay contributions. And this is, you know, it's a favorite question in all conferences. People are asking experimentalists how they are doing that. And you can hear a slightly different answer. I'm curious, what is your answer? How you're doing subtraction of decay for unmeasured particles? Something like, for example, omega, eta prime, because definitely experimentally you cannot know reliably their multiplicity and so on. How the procedure works in this case?
Okay, in ELIS we measured by 0, eta, omega.
How you measure omega? What is the omega you measure?
Omega in 3-pion decay channel was measured in PP collisions. It is for LED it was not published yet, but in PP it was published. And okay, if we compare spectra of all these light mesons, we see that they at high PT they follow the empty scaling. But at low PT, they start to break the scaling, and one have to be careful and look at different possibilities, possible behaviors. But fortunately, contribution of omega is only 2–3% depending on PT, and at low PT it is even negligible. Eta prime it is well below 1% contribution to decay. So it is still it is much smaller than other systematic uncertainties, for example,
yes.
from by 0 measurement. So what is important is to measure by 0 and eta.
Yeah, I know, but it's concerning the relative contribution to the direct photon spectra. But since we wanted to subtract and obtain finally the value, which is very small and few percentage from the total yield, so such type of corrections are getting important. And in some sense, it's also related to the fact that omega, what you can subtract from MT scaling or from measurement in proton-proton collisions, related to the final stage omega, where the emission of photon occurs during the time evolution of your fireball. And this is a kind of creation or recreation of these resonances. They still emit photons, but in some sense, it's not the final omega which comes to your detector. So, and another even worse question, because what you definitely cannot subtract, it's a Bremsstrahlung process. And as you know, you showed result from PhD approach where we made really point that the spectra actually can be described to a good extent also by the hadronic contribution, in particular Bremsstrahlung, because they point that Bremsstrahlung can contribute only at very low QT does not hold. If you just can make a simple estimates, what is the square root of S distribution of your let's say collisions, meson baryon collisions, or or baryon collisions, you cover rather wide range in square root of S. And yeah, and then this plot which you have shown, yeah. So this Bremsstrahlung plays a rather big role and comparable with QGP contribution. So how to deal with these things?
So I'm sorry, you are talking about the prompt photon Bremsstrahlung?
Yes,
or...
yes, I'm talking about, yeah. I'm talking about contribution from hadronic channels to your measurement, to interpretation of your measurement on prompt photons, yes.
Still, I'm a bit confused. So let's translate to my language. We have prompt photon contribution, which comes from interaction of partons contribute, okay, but is from incoming nuclei. Or we have interactions of hadrons in the final hadronic gas.
Right.
So which one do you call Bremsstrahlung?
Bremsstrahlung I call final hadronic stage of reaction. Unfortunately, still your hadrons can scatter with each other and emit photons, just standard Bremsstrahlung diagrams. And here that is depicted like violet line and blue line, which is rather huge.
Okay, but it is a normal thermal radiation from hot matter. So why should we separate it from 2-to-2 processes? So it is a normal emission of thermal photons from hot matter.
But it's not a thermal process. That's precisely a point. So I just want to say that unfortunately, as it turns out, so the photons which were initially assumed to measure directly the quark-gluon plasma emission suffer from these diseases that hadronic contribution in the later stage of the reaction also plays a rather important role. And unfortunately, also the V2 comes to largest extent from also the final stage. And yeah, unfortunately, that is a reality. And experimentally, I think that's precisely my point. You have no chance to subtract this contribution of just Bremsstrahlung, which nobody is interested in. Even if you have fantastic result and super fantastic accuracy of your measurement now, so about experimental part, no doubt that it's getting better and better. Yeah, but it's just more question, more remark might be to the interpretation of the data.
Okay, once more, it is a normal contribution from thermal emission. You have, okay, in sun, in hot QED plasma in sun, you have this Bremsstrahlung emission. And why should we separate them?
No, you should not. You should not separate them. But you can. I mean, you cannot. But the goal of the full story was a hope to see the thermal radiation directly. But it turns out that you have another, let's say, unwanted contributions. That's what I wanted to say. It's unfortunately which cannot be separated.
From my point of view, this Bremsstrahlung and two processes have a well-known relative contribution, and if you really wish to separate them, we can do it theoretically.
I don't think so, because precisely the Bremsstrahlung contribution to compute with the full glory, it turns out it's a rather difficult issue. There is no good theoretical model for this, and that turns to be a rather complicated story. And many theoreticians are trying now to attack this problem.
So
but okay.
Are there backgrounds for the photons, or they are not backgrounds? The question is this. So clearly, counting the number of photons at one state, is it clear indication of the picture, what there happens? One mechanism or several mechanisms? So Elena stated that there may be different mechanisms which each one makes a background for the others. It's not good, surely, but at very early, at the perturbative stage, we know just by diagrams which quarks radiates which photons and so on. So there is clear picture, surely. Nothing can make backgrounds to that. Later, maybe there are big backgrounds, and that photon picture of the processes may be not very clear. But I prefer that they are clear. But it's just wish, just hope. Thank you.
Yeah, but what I think, so it's a, how to say, it's in some sense it's not background, and it's a physical process which contribute to the direct photon measurement, and we have to stay with that. But might be measurement of V2 and more precise correlations would help somehow to separate the wanted signal of quark-gluon plasma, and that's what was the ultimate goal and interest of all people, and not to measure such boring things. Yeah,
at least we may estimate from, if we have some number of photons, we can say that something of that may be ALD photons, others are backgrounds. If we know how to calculate that wrong photons as a background, we can subtract that number. I'm not sure that we can calculate.
Okay, thank you. Do we have some other question to Dmitri? I don't see other hands. Maybe it's really getting a little bit late. Oleg Teryaev, please, Oleg.
Just a short, I don't know, question or comment concerning just PT spectra. I see that typically all the dependence is an exponential one. And if to compare, just considering small systems and compare just AA and say PP, well, there are there is no there is no temperature in PP, but there are some thermal model of Parton distributions. And at some point, maybe 10 years from now, we speculated a bit that this may be considered as a sort of I don't know, duality between statistical thermal description and dynamical QCD description. I wonder maybe just a specific point, maybe use of thermal models for Parton distribution can a little bit explore these relations between temperature and just PT. So this is just a suggestion. I really don't know how this may.
Okay, Alec, indeed, all spectra measured in PP collisions and especially in AA collisions are better fitted with a two-component model, which includes this thermal plus parallel tail. So indeed, spectra better described, but to which extent this exponential, how seriously should we take this exponential contribution, I'm not sure.
Well, so but in principle, well, it's this model is not. I mean, thermal model of Parton distribution is not so popular, but it appears that it provides the same chi-square for that it can be used. And in this, in terms of just physical quantities, maybe if one like to describe PP in say some thermal context, this may be used. That we just tried, but just not very active. Okay, this is just.
Okay, Alex, thank you. And Dmitry, thank you very much. I think we now come to Chihiro talk. And in this case, Chihiro, can you maybe share your slides? Yes, very good.
You have a couple of questions.
Yes,
very nice.
Yes. So maybe let me see if I see other hands on the moment. So. Well, maybe people are thinking still because let's say let me maybe ask a few questions.
Yes.
And I was a little bit precisely wondering about the sharp spectral function which you obtain for phi meson. And because it has some kind of very abrupt structure, yes, and it turns out that you consider only 2K threshold, but in principle phi we know can decay to 3 pions, to pi, to rho pi, and go masses practically to 0, it's pi gamma and so on. Why it is not counted, or what is? Can you comment?
Yes, because I did not incorporate fully, I mean, in medium version of the spectral function of phi. I simply multiplied by constant factor here. So therefore, of course, in reality, you are completely right that this the abrupt change should be gone.
Okay. So it's just artifact of
yes, this is just an artifact of my simplified calculation.
Okay, good. And maybe I ask other question because you know this issue of the mixing of rho and A1 has been addressed in the paper of Holler and Rapp. It was, if I remember, 2016 or something
Yeah,
like
maybe
that.
this one,
Ah,
yeah.
yeah, exactly. Yes, yes, exactly this paper. Can you comment maybe what is the
Yes.
main difference
Okay.
between your
All right.
approach and their approach?
Okay, so first of all, they consider the type of chiral mixing, which is totally different from what I have considered. So they consider the chiral mixing based on the Eletsky-Joffe theorem. This is more relevant for the hot matter. Okay, and then maybe it's a good idea to remind all of you about this low energy theorem.
Okay.
So they are the in-medium version of the vector and axial vector current correlation functions. And then it turns out that if your temperature is low enough and then only pions are thermally excited, and then this finite temperature version of the current correlation functions are expressed as a combination of the vector correlator and axial vector correlator at t equals 0. And then here, the finite parameter epsilon appears. This directly proportional to t square. And then this is called the mixing parameter. And this is the same quantity, but the diagrammatic the expression. And then from this formula, it's clear that some portion of axial vector spectral function should be present in the in-medium, the vector spectral function. So this is such an illustrative calculation. Yeah, okay, and then typically you have the two-peak structure. This one is the remnant of the raw meson, vacuum raw meson, and another much broader one. This is the contribution coming from the axial vector meson. So this is the standard one, and then like Ralph and others have been putting this contribution to refine the calculation of dilepton and so on. Right, okay, this mixing, so what's the difference from the mixing which I have considered? The main difference is that this mixing must be vanishing when the chiral symmetry gets restored. So the intuitive interpretation is that this must be, so the diagrammatically, this the mixing is induced by the vertex of pion, raw meson, and A1. This must be vanishing because otherwise the decay rates of A1 to rho pi, this channel cannot be closed. Okay, and then since the rho A1 must become chiral partner, so therefore this decay channel cannot be open. So essentially, in those papers, they have observed basically the same physics in terms of slightly different language. So they started with the vector spectral function, which was constructed by Ralph and his collaborators, and in which was confronted to the measurements. So therefore, so this is a good in-medium version of the vector spectral function. So the question is how to obtain consistently the corresponding in-medium axial vector spectral function. So for this purpose, they utilize the model independent relation sum rules. This is called the Weinberg sum rules for the raw meson, vector and axial vector spectral functions. And the sum rules, they are made of three sets of the equations. And they started with the well-defined vector spectral function with a couple of well-motivated ansatz or parameterization for the in-medium axial vector mass and the A1 decay width, and then they solve the sum rule self-consistently at the given temperature. By the way, this calculation was done entirely at zero chemical potential, only temperature effect was considered. And then, so that way, they succeeded to construct the axial vector spectral function at the different temperatures. And then, so this is the vacuum one, and then we see clearly the typical the structure, which is perfectly consistent to the Eletsky-Joffe mixing. And then when the temperature is gradually increased, first of all, you see that the substantial reduction of the axial vector meson mass, right? So this temperature is corresponding to the chiral, the crossover, because in fact, two spectral functions, they are more or less degenerate, together with the broadening of the decay width of both A1 and the raw mesons. So this is what they observed. So the message is, as I said, the mixing parameter is essentially vanishing. So that's why eventually at the chiral crossover, you have single maximum brought the maximum. So this is the difference. And then this mixing effect becomes important, as I said, at the small chemical potential, finite temperature. On the other hand, the different type of mixing induced by the Chern-Simons term, which I have talked about, is not relevant at such a hot matter, but it becomes very relevant if the temperature is low enough, and then the typical net baryon density is a few times of the saturation density.
Yeah, okay, thank you. I think it would be really relevant for Nika and fair activity. Yes.
Yes.
Okay, thank you, Chihiro. So please raise your hand if you want, if you still have questions. Yes, Oleg, please. Oleg.
It is old hand.
If there is a
new one.
Yeah, in the case of external, say, magnetic field, it can be mixed correlator containing vector and axial current.
Okay.
Is it really possible to look for it, or can it somehow?
Yeah, okay, so far I did not consider
here?
any external magnetic field, and then as you said, this once it's included, this will become another source of the chiral mixing. But I have not checked yet that if such a mixing becomes enhanced, just like the chiral mixing induced by density in nuclear matter, as I have discussed. This needs to be checked.
Okay.
Okay. I think we are really a bit late. I see no other hands. And I think we thank Chihiro very much.
Thank you very much.
Thank you very much. And we come to our last topic of the discussion about lambda polarization. Evgeny, are you with us?
Yes.
It's perfect. Can you share now screen or your slides, or should
Yes,
I
yes.
do that?
No, I can share. I hope so.
Yeah, super. Yes, very good. And well, please prepare your questions to Evgeny. I see the hands of Oleg. Oleg, it's old hand or new hand?
It's permanent.
Permanent. Okay, just go ahead.
But he's on mute.
It may be considered as my uploading, but maybe I was already asking Evgeny, what do you think how robust is this result? So is it possible? So of course it is different. I mean, the production of anti-lambda and lambda, but is it really like it appeared? So can it be, say, vice versa? So its polarization will be lower, or is it a robust prediction? This is my question for polarization.
Well, from the model point of view, it's quite robust.
You mean in the model in UND, but maybe in another model, can it be something different, or
something different?
Opposite? Because can one say imagine that in some model it will be opposite, or there are some general reasons that it will be more
Oleg,
or less
I'm very sorry, can I
almost.
penetrate? Of course, you might be construct some absolutely crazy model, but in this case, everything could happen, of course. But we are discussing realistic model which could describe a heavy ion data, and that is a key point. And definitely we know that your QMD can describe the data. And in this case, it's very hard that it's fully wrong.
No, I mean, for example, if you take other model describing the data, like your model, is it
it's
reasonable?
actually yes, it's actually it was a work by also Vadim Voronyuk and Vyacheslav Taneyev and Evgeny Kolomeyev, right. So, and in this case, they obtained rather similar result with PhD. Yes.
Also different just time, yes, because I know this about this work, but I didn't. So this is also provide a larger polarization because I actually remember some talks, some discussion with Vadim, And he didn't produce the polarization of lambda bar higher than lambda.
That's a little bit higher, but not. It definitely doesn't come to 8%. Similar as Evgeny showed. It's a little bit higher, but not so high.
Maybe also because right now I have time to say a little bit more. You see, it was when we submitted this paper for publication, we got very interesting question from the referee who mentioned that, look, guys, you took lambdas directly produced and lambdas, yes, or lambda bars coming from the decay of sigma hyperons. And you took essentially the same polarization in both cases. Whereas there are a couple of papers, for instance, one of the papers by Francesca Beccatini, Mike Lisa, Sergei Voloshin, and somebody else, they show that in case of sigma decay, for instance, sigma 0 to lambda plus gamma, or sigma star to lambda plus pi, polarization of lambda in average should be, say, 15% lower. Yes, we agreed with this, but we checked not for all energies because it's very time consuming. We checked just for B equals to 6 Fermi and for 2 or right now maybe 3 different energies. Traces back when lambda is produced as a result of sigma decay, we traced back to the point where sigma experienced its last interaction, or it was produced. Since sigma has a certain lifetime, non-zero lifetime, it was produced earlier when it decays, definitely. And at that time, the vorticity of the area when sigma was produced was larger. So these two effects, somehow they cancel each other. So the total correction to our result was less than 4%. Not the polarization in percent, but 4% of our 3, say, or 2%. So it was negligibly small. So we checked different effects which can cause the rise or vice versa decrease of lambda bar polarization.
Evgeny, can I ask you, but
Yes,
I
yes,
think
sure.
you have dynamical decay of all these higher resonances because there are a couple of higher baryon resonances in UQMD, sigma star, whatever, so then higher lambdas with some crazy number. So they all decay to lambda, and that is dynamically counted, right?
Yes. But the question was that if in this case, when they decay into lambda, then polarization of daughter lambda should be decreased a little bit.
Yeah, that's I understand.
Yes.
But how your decay occurs? Is it isotropic or in this case? Or...
No. Decay is isotropic. We didn't modify the internal block of URQMD, but we traced, in this case, we traced back a little bit further to the last interaction point of decaying particle, of mother particle. And then it appears that the vorticity of the matter in this region and at this time was larger, yes, compared to when it was decaying, vorticity of medium when this particle was decaying. And these two effects, so larger vorticity and then lowering of lambda polarization, they were eating each other. So that's we checked.
Okay, thanks. Are there some other questions? If you have questions, please raise your hands. Maybe Evgenia, I still have a question because by seeing your result, I'm kind of have the following question because in the PHSD calculation, of course, we took into account the contribution of quark-gluon plasma and so on, and definitely it changes the dynamics of heavy ion collision substantially. And in this case, one would naively expect that your vorticity would be rather different. And since vorticity coupled to lambda polarization, you would expect some different result for lambda polarization. But it turns out that results of UQMD, which you presented here, which is just pure hadron string model, right, is rather similar to the result of the PHSD, where definitely quark-gluon plasma has been taken into account. And in some sense, the message is, does it mean that this observable is rather insensitive to the internal dynamics, or it's a coincidence? What is your feeling in this direction?
Well, but first of all, we expect that larger volume of QGP will be produced in central collisions and at relatively.
You're right, maybe you're right. Yeah, you're
here
right.
We are talking about 6 or even 9 Fermi. So
Thank
here,
you.
the influence of plasma is.
In this case, our models are rather
Yes.
similar. Yes, it's not big surprise that they have similar results. Okay, maybe I ask you still one question. It's related to the subtraction of the temperature and baryon chemical potential, because if I understood, you use this old procedure when you solve the system of couple equation, when you compute the energy density in UQMD and baryon density, strange density, and then solve this couple equation and subtract by that temperature and baryon chemical potential and strangeness potential. So, but my question is, if you just, the point is, some cells are definitely can be out of equilibrium, right?
Yes.
And if you just take this temperature and just compare the slope of expected, let's say, expected slope of hadrons with this temperature and the real slope of hadrons in your UQMD simulations, how differ they are? Did you? I think you made this check, if I remember, with Larissa. Yeah.
Yes, they are quite different, but also
they're different, right?
You're quite right. Yes. So if our system is out of equilibrium, there is no rigorous way to define the temperature.
Absolutely.
Definitely, we can put this. We can in the solver. We can get a T mu B mu S, but that's why during my talk I mentioned this. Finally, one has to compare the spectra, yes, energy spectra or yields of particles. If they are close to each other, yes, we are close. If not, well, but you see, so to speak, when people are using it, first of all, I also mentioned that this method, this mathematical apparatus worked out by Becattini, it's obtained under the assumption of local equilibrium.
Exactly. That's precisely what
If
was
we are out
my
of
next
equilibrium,
question.
well, the room is open and nobody knows how to proceed correctly.
Okay, thank you. I see the hand of Nuxar as usual, so please.
Yes, at last the question appears. We have seen that for air-list photons, we know the processes, just diagrams. Can you show the process at which appears first lambda bar? Air-list pair. By diagrams we can draw, but very tricky diagrams.
I mean, lambda bars, but we are not.
Simplest
well, lambda,
process.
I can, for lambda, I can suggest you very easy process, since we are talking about relatively low energies. Lambda, imagine that out of proton, you're excite proton. You're producing a string, quark, diquark. d quark on one side and di quark ud on the other side. Now, as a string is stretching a little bit more, you are producing strange anti-strange quark. And after breakage of the string, you got lambda, UDS core, S, yes, baryon, and K plus, U anti-S. So that's the process, for instance, how to produce lambda, quite easy. To produce a lambda bar, you see, you have to produce 3 anti-quarks. And it's not, this is not so easy process.
Someone calculated the diagram contributions for lambda and then lambda bar. Are there estimations for that cross sections?
Yes, of course, and even there is a measurement. Sorry, interrupt you, Evgeny.
Yes, yes.
Yes, and it's realized also in Evgeny case in terms of strings.
Okay.
But if you think about very low energy, I can propose you the following process. Nucleon goes to nucleon, hyperon, and kaon. You have to conserve strangeness.
Yes.
And that is a typical process for hyperon production at low energy, and this has been computed in many models.
And what is the contribution of that fast? How significant is it on 1% or 10% or?
It depends on the
90?
collision energy.
Mm-hmm.
Because this process which Elena mentioned, nucleon, then say lambda hyperon and pion or kaon, kaon, yes, it's quite important in this energy range between say 4, 5 GeV in the center of mass frame up to 15 maybe. Yes, this process is very important.
We have definitely answer for that fast processes, and somewhere we can identify kinematics where that contribution dominates.
Mm-hmm.
Or background is minimal.
Yes, if you have the right analytic solution, then it's no problem to compare with, say, Monte Carlo model results. Because in Monte Carlo, all processes are allowed, and then
yes, Monte Carlo models the calculation, but in experiments you have cross sections for the experimental cross sections for the lambda.
But we use in QMD, we use all available experimental data for the cross section of hadronic processes. Sure.
And you know the region of parameters where that fast process dominates significantly. Okay.
So it's
nice.
Everything is tabulated if possible.
Because if you have so clear process, you can test there many things.
Yeah, of course.
Nuclear densities we cannot test. We just take from other processes. Okay. Thank you.
Thank you, Evgeny. I think we are late by 15 minutes, and it's really should be rather late. But thank you, Evgeny, very much. I don't see other hands. And I think everybody is a bit exhausted after this long day and long discussion. In the end, I would like to thank all our speakers and thank you everybody for participating in our discussion session. And I still wish you a good evening and say goodbye.
Goodbye. Thank you.
Bye. Good night.